So I read that parastatistics existed since the dawn of quantum mechanics.
Yeah.
And some of the early work on paraparticles came to the conclusion that any such theory is physically indistinguishable from theories of ordinary fermions or bosons. So walk us through these series of developments and what is it that makes paraparticles so elusive?
Yeah, this is a fascinating history because there have been a lot of near misses with paraparticles where people sort of thought they discovered them or maybe even did discover them in some sense, but later it was realized they were sort of the same thing as fermions and bosons. So it was in the sort of 20s and 30s that people began to see fermions and bosons as these two natural classes of particles, and they got the names of the people who started realizing this, for Bose-statistics and Fermi for fermions, Enrico Fermi. And then in the 30s, you already see people starting to wonder what else could be there. Because essentially, these two possibilities that you get a minus sign when you swap particles or you get a plus sign, you could start asking things like, well, what if I have three particles, I swap two of them, I get a minus sign, I swap the other two, I get a minus sign, but this pair has a plus sign. Maybe I could mix things up like that. And maybe you could do other generalizations of this. And so this question, you can read in like Pauli's Nobel lecture or Dirac's Nobel lecture, they both mention this problem that there seem to be fermions, bosons, and a whole zoo of other possibilities. And in these articles, they just kind of go, well, they don't seem to be realized in nature. Okay. And later, people started thinking more about this, and in particular, in 1953, I believe, Green started to study this problem. And so Green found a theory of parastatistics.
And which Green is this?
This is Herbert Green, I believe, and you'll have to edit my voice to the proper name if I forgot his name. But if I remember correctly, he was a mathematician somewhere, or a physicist somewhere in Australia thinking about these sorts of problems. And he was thinking about them, and he found these new types of particles in which he wrote down a complete theory. You could solve its behavior. It looked sort of similar to our normal theory of fermions and bosons, but modified, and there was parastatistics for the first time. Except it turned out, later realized, that it was fermions and bosons in disguise. So people realized that for any physical measurement you could do, you could spoof the measurement with fermions or bosons. You could get exactly the same thing from fermions or bosons. And so it's still an interesting mathematical theory. It may give you a different perspective on certain types of fermion and boson problems, but at the end of the day, it's equivalent to them. And this was later in the 50s, I believe, Greenberg and Messiah started thinking about the color degree of freedom, what we now would think of the color degree of freedom in quantum chromodynamics for quarks. And they were actually trying to understand this by thinking about it as this parastatistical label. And then again, in hindsight, their theory is equivalent to some theory of fermions and bosons, so it's not necessarily new, but, they were starting to think about applications of this. And so there was a lot of excitement, but also ultimately this weird question that, okay, Dirac, Pauli, and others said, here's this new class of potential particles. Here's people wrote down theories that sort of seem to realize some interesting class of this, but then actually it didn't work. They were fermions and bosons. Why? So this was kind of a mystery. And so in the 1970s, the mathematical physicists really got a hold of this. And so there's a series of articles by Dupliker, Haag, and Roberts that goes by the name of DHR theory. It's now sort of established theory, which the sort of layman, by layman I mean 99% of physicists here, interpretation of this paper is that it says the only types of particles possible in three dimensions are fermions and bosons. And that seemingly put the nails in the coffin until 2023 when we found this stuff.
I see. So how did your approach sort of actually got a grip on what was happening?
Great. So there was massive ignorance on our part, which helped. So we didn't know that much about DHR theory, or maybe Zhuan did, but I didn't. And so I was happy to charge on in just saying, well, nobody's proved that this can't happen. And so that was our initial impetus to get things going. But how did we actually circumvent this stuff? It turns out that the theorem doesn't say what everyone sort of claims it says in this one sentence version. What it actually says is that for particles that are not remotely detectable, they can only be fermions and bosons. And so this idea of remote detectability just means if you have a detector at infinity, then you can't see stuff that's far away. You can't see stuff away from that detector, right? So that would mean that you do not have remote detectability of this particle. And so people say that's like locality. So if you want a local theory, you don't want influences to propagate infinitely fast or, faster than the speed of light or something, then maybe you don't want remote detectability. And so they showed with no remote detectability, you got fermions and bosons. But no remote detectability is actually a stronger requirement than locality. So let me give you an example. Okay. And it's an example from freshman physics. So if I take a charged particle and then I build a giant detector at the sort of edge of the universe or very far away, I can detect that particle through Gauss's law.
Right.
I know that there's a net flux through my detector.
Right.
This doesn't violate causality, locality. It doesn't violate anything. It's just how charges work. And in fact, anions, which have been known about since the 1980s, which exist in 2 dimensions and violate fermionic and bosonic statistics, they also are remotely detectable. So the fact that with no remote detectability you couldn't have anything other than fermions or bosons really maybe didn't say all that much. Right. It's a very important theorem. It certainly classifies a broad class of interesting situations, but it's not the end of the story. And I think there's certainly nothing wrong with considering particles that are remotely detectable, just like charges and anions are.